Hello, and welcome to Science After Dark, the place where the mysteries of the universe unfold in the most intriguing and calming way possible. If you're fascinated by the cosmos, be sure to like and subscribe so you never miss a journey into the stars. And while you're here, we'd love to hear from you. Where are you watching or listening from? Whether you're cozying up under the night sky or relaxing in the comfort of your own space, feel free to share your location. Perhaps you're stargazing from a place that's seen its own share of cosmic wonders. Tonight, we're diving into one of the most exciting frontiers of modern science, exoplanets. These distant worlds, orbiting stars far beyond our solar system, are not just remarkable because of their distance, but because of what they could reveal about life, the universe, and our place within it. Could there be other Earth-like planets out there waiting to be discovered? Are we truly alone, or are there other civilizations beyond the stars? Settle in, because tonight we embark on a journey to explore these fascinating worlds that might hold the answers to some of humanity's oldest questions. So, let's begin. When we look up at the night sky, it's easy to think of the stars as distant, untouchable points of light, each one unique and far beyond our reach. But what if we told you that some of those stars might be surrounded by planets that we've only recently begun to discover? These planets are called exoplanets, and they're changing the way we understand the universe. An exoplanet is simply any planet that orbits a star outside our solar system. While we've known about the planets in our own solar system for centuries, exoplanets are a relatively recent discovery. The first confirmed exoplanet wasn't found until 1995, when astronomers Michel Mayor and Didier Queloz detected a planet orbiting a star called 51 Pegasi, located about 50 light-years away. It was a groundbreaking discovery that opened up a whole new realm of possibilities for understanding the cosmos. But why are exoplanets so significant? Well, they're more than just distant worlds to study. Each exoplanet holds secrets about how planets form, how they evolve, and whether life could exist beyond Earth. They provide us with a broader perspective on what makes a planet habitable and what conditions might support life elsewhere in the universe. As we delve deeper into this fascinating topic, it's important to understand that the discovery of exoplanets ties into much bigger questions about the universe itself. One of the key figures in modern cosmology, Vera Rubin, didn't directly study exoplanets, but her groundbreaking work on the movement of galaxies laid the foundation for our understanding of the universe's structure. In the 1970s, Rubin discovered that galaxies were spinning at such speeds that they should have torn themselves apart, but they didn't. This led her to propose the existence of dark matter, a mysterious substance that doesn't emit light but has mass and gravity, influencing the motion of galaxies. While her research was focused on the larger structure of the cosmos, it indirectly helped set the stage for our understanding of planetary systems outside our own. Her work reminded us that there's still so much more to learn about the forces at play in the universe. Exoplanets are central to this expanding view of the universe. They offer a way to understand how stars form, how planets are born from the material that swirls around them, and how these planets might end up with atmospheres, water, and the potential for life. Every new discovery of an exoplanet reveals something important about the universe's history and its future. Some of these planets are very similar to Earth, which raises fascinating questions about whether life could exist elsewhere. Other exoplanets are vastly different, with extreme temperatures, massive storms, and unusual compositions. They challenge our understanding of what's possible, forcing us to rethink everything we know about the conditions needed for life. But before we can appreciate the vastness of this discovery, it helps to understand how we even found these distant worlds in the first place. The journey to discovering exoplanets didn't begin in 1995 with the groundbreaking work of Mayor and Queloz. It began long before, with a series of experiments, theories, and ideas that laid the groundwork for understanding how planets could exist around other stars. In fact, astronomers have been speculating about the existence of planets around other stars for centuries, even if they didn't have the technology to prove it until much later. The earliest hint of the possibility of exoplanets came in the form of a simple yet profound question. Do other stars have planets, just like our Sun has planets? In the early 20th century, astronomers began to recognize that stars were not solitary objects but part of much larger systems. The idea that other stars might have planets seemed almost inevitable, and yet, for many years, it was purely speculative. It wasn't until the 1990s, as technology advanced, that astronomers were finally able to detect these planets, starting with the discovery of 51 Pegasi b. This was a huge breakthrough, but the search didn't stop there. The more we discovered about exoplanets, the more we realized just how diverse these planets could be. Some exoplanets are gas giants, similar to Jupiter, while others are rocky like Earth, and some even have the potential to support life. One of the most exciting aspects of exoplanet discovery is the ongoing search for planets that are similar to Earth, often referred to as Earth-like exoplanets. These are planets that lie within a star's habitable zone, the region where conditions are just right for liquid water to exist. Liquid water is considered essential for life as we know it, so finding Earth-like exoplanets in habitable zones is one of the primary goals of modern astronomy. As we continue to discover more exoplanets, we're not only expanding our knowledge of distant worlds, but also shaping our understanding of what makes our own planet so special. The study of exoplanets allows us to ask profound questions about our place in the universe. Are we truly alone, or are there other planets out there that harbour life? Could we one day travel to these distant worlds and establish a new home? The discovery of exoplanets isn't just about finding new worlds. It's about understanding the forces that govern the universe, the processes that lead to the formation of planets, and the potential for life to exist elsewhere. Each new exoplanet discovery is a piece of the puzzle that helps us better understand the cosmos, from the smallest star systems to the largest galaxies. So, as we embark on this journey of exploration, keep in mind that every exoplanet we discover brings us one step closer to answering some of the universe's most profound questions. Whether these planets are small, rocky worlds or gas giants, they help us piece together the grand story of how planets form and evolve. And as we explore this vast, exciting frontier, we're not just looking at distant stars, we're looking for the key to understanding the universe itself. The idea of planets existing beyond our solar system has fascinated astronomers for centuries. In fact, the concept of exoplanets, as we know them today, was first proposed long before we had the tools to find them. The earliest whispers of exoplanets began in the early days of astronomy, when scientists first realized that stars were not solitary points in the sky, but rather part of vast systems, much like our own Sun. The possibility that other stars could have planets orbiting them seemed almost inevitable, but proving it was another matter entirely. As far back as the late 1800s, astronomers began speculating about the existence of planets orbiting stars other than our Sun. In the early 20th century, astronomer Jules Verne imagined the possibility of other solar systems, an idea that helped set the stage for future thinking. But despite the speculation, actual evidence for exoplanets remained elusive for many years. One of the first major milestones in exoplanet research was the establishment of reliable distance scales that allowed astronomers to measure the distances to distant stars. Prior to these advancements, we could only estimate the relative distances between stars, which made it almost impossible to detect the subtle movements that might indicate the presence of orbiting planets. In the 1970s, Wendy Friedman, an astronomer and physicist, made significant contributions to improving distance measurements. Friedman played a key role in refining the technique known as Cepheid variable stars to help calculate distances in the universe with greater accuracy. These measurements allowed for better understanding of how far away other stars were, which in turn made it possible to begin the search for planets beyond our solar system. While her work didn't directly lead to the discovery of exoplanets, it provided a crucial foundation for future efforts by making the stars, and their planets, more measurable. The speculation and early scientific efforts to explore the idea of exoplanets weren't just limited to technical advancements. Throughout the 20th century, many prominent scientists contributed ideas that would lay the groundwork for the discovery of exoplanets. Among them was Fred Hoyle, a British astronomer who is best known for his contributions to the theory of stellar nuclear synthesis, or how elements are formed in stars. Hoyle, however, was also deeply interested in the possibility of life existing elsewhere in the universe. In his work, he speculated that the universe might be teeming with life, and that planets outside our solar system could support this life. He was one of the early proponents of the idea that life on Earth might not be unique, and that other planets, even those far from our Sun, could have similar conditions for life to flourish. Hoyle's work, while focused on the broader cosmic scale, shaped the way scientists thought about the potential for planets to exist around distant stars. even though direct evidence was still out of reach. As the years passed, technology began to evolve, and the idea of exoplanets transitioned from speculation to a more realistic possibility. During the 1980s and 90s, astronomers began to develop increasingly sophisticated techniques to detect the subtle influences of planets on their host stars. One of the most significant breakthroughs came with the development of the radial velocity method, a technique that allowed astronomers to detect the gravitational pull of an orbiting planet by observing the slight wobble of its parent star. This wobble is caused by the gravitational tug of the planet as it orbits the star, shifting the star's light slightly toward the red or blue end of the spectrum. By measuring this shift, astronomers could infer the presence of a planet. In 1995, two astronomers, Michel Mayor and Didier Queloz, achieved what was once thought impossible. They discovered the first confirmed exoplanet, 51 Pegasi b, orbiting a star similar to our Sun. This was the moment that exoplanet research moved from the realm of theory into the domain of real observable science. 51 Pegasi b was a gas giant, much like Jupiter, but it orbited much closer to its star, making it an ultra-hot Jupiter. Despite its hostile conditions, its discovery marked the beginning of a new era in astronomy. The technology and techniques for detecting exoplanets continued to improve. As astronomers began to detect more and more exoplanets, they realized the immense variety of planets out there. Some were gas giants, others rocky like Earth, and some were even closer to our understanding of what we might consider habitable. The Kepler Space Telescope, launched in 2009, dramatically expanded our ability to detect exoplanets. It used the transit method, a technique that involved measuring the dimming of a star's light when a planet passed in front of it. By observing this tiny dip in brightness, astronomers could not only detect the presence of a planet, but also measure its size, orbit, and, in some cases, even its composition. Kepler's discoveries brought us closer to understanding how planets form and how diverse these planets can be, including the discovery of Earth-like exoplanets in the habitable zone, regions around stars where conditions could support liquid water. Kepler's impact on exoplanet research was immeasurable. By the time it completed its primary mission in 2018, it had confirmed the existence of thousands of exoplanets, some in or near the habitable zone, raising hopes that one day we might find another Earth-like world. But even with this wealth of discoveries, the search for exoplanets continues, as astronomers strive to learn more about these distant worlds and their potential for harboring life. The methods we use to detect exoplanets have evolved significantly over time, and they continue to advance as technology improves. New techniques, such as direct imaging and gravitational microlensing, are allowing us to detect planets in increasingly distant and faint systems. Direct imaging, for example, involves capturing an actual picture of an exoplanet by blocking out the light of the host star, revealing the faint glow of the planet itself. Gravitational microlensing, on the other hand, takes advantage of the gravitational lensing effect, in which a planet's gravity bends the light from a more distant star, creating a brief but measurable change in the light curve. These new methods are expanding our ability to find exoplanets, particularly those that are far from their stars and harder to detect using traditional techniques. As we look to the future, the next great leap in exoplanet discovery may come from the James Webb Space Telescope, which is set to launch soon. Equipped with powerful infrared capabilities, JWST will allow us to peer deeper into exoplanetary atmospheres than ever before. We'll be able to study their chemical compositions and perhaps even identify signs of life, such as oxygen, methane, or carbon dioxide. The data from JWST promises to revolutionize our understanding of exoplanets, providing more detailed and accurate information about these distant worlds. The history of exoplanet discovery is a testament to the power of human curiosity and the relentless pursuit of knowledge. What began as a mere idea has grown into a vibrant field of scientific inquiry, one that holds the key to answering some of humanity's most profound questions. As we continue to explore the cosmos and uncover new exoplanets, we are not only learning more about the universe, but also about ourselves, our place in the universe, and whether we are truly alone. The search for exoplanets has been a journey that requires ingenuity, patience, and a deep understanding of the cosmos. In the beginning, detecting planets outside our solar system seemed like an impossible task. After all, how could we see a tiny planet orbiting a star that could be hundreds or even thousands of light years away? but through decades of scientific advancement and the development of clever techniques, astronomers have found ways to observe the faintest signs of distant planets. One of the most significant breakthroughs in the search for exoplanets came from the radial velocity method, sometimes referred to as the Doppler method. This technique detects the tiny wobble of a star as it is affected by the gravitational pull of an orbiting planet. When a planet orbits a star, it causes the star to move in a small orbit of its own. This movement is extremely subtle, but it has a direct impact on the light we see from the star. As the star moves toward us, its light shifts toward the blue end of the spectrum, and when it moves away from us, the light shifts toward the red end. This effect is known as the Doppler shift. By measuring this shift in the star's light, astronomers can infer the presence of a planet, even if that planet is too faint to be seen directly. The first confirmed exoplanet discovered using this method was 51 Pegasi b in 1995. The planet's gravitational tug on its star was enough to cause a measurable wobble, and through the Doppler shift in the light, astronomers were able to confirm its existence. This was a monumental moment in astronomy because it not only proved that exoplanets exist, but also opened the door for more advanced and refined techniques. Another method that has become increasingly important in exoplanet detection is direct imaging. While the radial velocity method measures the star's movement, direct imaging captures an actual picture of the planet itself. This is an incredibly challenging task, as the star is typically many times brighter than the planet. To overcome this, astronomers use special instruments that block out the light from the star, revealing the faint glow of the exoplanet. The first successful direct imaging of an exoplanet came in 2008, with the discovery of Fomalhaut b, a planet orbiting the star Fomalhaut, located about 25 light-years from Earth. Direct imaging is particularly useful for studying young exoplanets, which tend to be hotter and more easily detected in infrared light. While both radial velocity and direct imaging are incredibly powerful methods, they still have limitations. For example, radial velocity works best for detecting larger planets that are close to their stars, while direct imaging is limited by the brightness of the star and the planet's age. This is where gravitational microlensing comes in. Gravitational microlensing is a technique that takes advantage of the gravitational field of a foreground star, which acts like a lens, bending and magnifying the light from a more distant star. If a planet is orbiting the foreground star, it will cause a brief but detectable change in the light curve, allowing astronomers to spot the planet. This technique is useful for detecting planets that are farther from their stars, and can even help find planets that might not be visible through other methods. The first exoplanet discovered using microlensing was in 2010, and since then, this technique has been used to detect thousands of potential planets. In addition to these methods, the work of Lyndon Bell, a British astrophysicist, helped provide the theoretical underpinnings for the detection of exoplanets. Lyndon Bell's theory of stellar dynamics described the way that stars and their planets interact gravitationally, influencing how they move through space. This understanding helped astronomers better predict where planets might be located and how they might affect the light coming from their stars. His work was crucial in expanding the understanding of how planetary systems form and how their motions can reveal their existence. Another key figure in the development of exoplanet detection was Hilary C.D. Alcock, whose research on planetary atmospheres advanced the techniques used to study exoplanets. Alcock's work focused on analysing the light that passes through a planet's atmosphere as it transits in front of its star. When a planet passes between its star and Earth, some of the star's light filters through the planet's atmosphere, and by studying the light's composition, astronomers can learn about the planet's atmosphere. This technique, known as the transit method, has been instrumental in identifying potentially habitable exoplanets. The Kepler Space Telescope, launched in 2009, used the transit method to discover thousands of exoplanets. By measuring the tiny dips in light caused by a planet passing in front of its star, Kepler was able to identify planets as small as Earth and in or near their star's habitable zone. This brings us to NASA's Transiting Exoplanet Survey Satellite, or TESS, which is the most recent mission dedicated to finding exoplanets using the transit method. Launched in 2018, TESS is designed to survey nearly the entire sky and detect exoplanets around the brightest stars visible from Earth. TESS is particularly focused on finding exoplanets that are within reach of follow-up observations by larger telescopes, such as the James Webb Space Telescope, which is set to launch in the near future. JWST's powerful infrared capabilities will allow it to study exoplanet atmospheres in unprecedented detail, potentially revealing the chemical signatures of life. Each of these methods, from radial velocity to direct imaging to microlensing, plays a crucial role in the ongoing search for exoplanets. They complement one another, and together they provide a comprehensive view of the incredible diversity of planets that exist beyond our solar system. Some planets are gas giants, others are rocky and Earth-like, and some have extreme conditions that challenge our understanding of how planets can form and evolve. These discoveries are helping us piece together the story of planetary systems and are transforming our understanding of the universe. As we continue to develop more advanced techniques and instruments, the number of exoplanets we discover will only grow. With the help of new space missions and telescopes such as JWST and future missions, we will be able to study exoplanets in even greater detail. We may one day even detect signs of life on these distant worlds, answering one of the greatest questions humanity has ever asked. Are we alone in the universe? The search for exoplanets is not just about finding new worlds, it's about understanding the broader forces that shape the universe. As we learn more about exoplanets, we're also learning about the nature of stars, the formation of planetary systems, and the possibility of life beyond Earth. Each new discovery brings us one step closer to unraveling the mysteries of the cosmos and our place within it. As we look at the growing list of exoplanets discovered over the past few decades, one thing becomes abundantly clear. The universe is home to a truly remarkable variety of planets. Each new discovery challenges our ideas about how planets form, what conditions they can endure, and how diverse planetary systems can be. From massive gas giants to rocky worlds, from planets that may host oceans of water to those that may not even be bound to a star, the diversity of exoplanets is both staggering and awe-inspiring. One of the first major surprises came when astronomers began to detect gas giants orbiting very close to their stars. These planets, similar to Jupiter and Saturn, were thought to form farther out in a star system, where it was cold enough for gases to condense and form massive worlds. However, the discovery of hot Jupiters, like 51 Pegasi b, shattered that assumption. Hot Jupiters are gas giants that orbit very close to their stars, sometimes so close that their surface temperatures can exceed thousands of degrees Fahrenheit. These planets challenge our understanding of planetary formation because, in theory, such large gas giants should not be able to form so close to their stars, where the heat should prevent gas from accumulating in the way it does farther out. The existence of hot Jupiters raises profound questions about how planets can form and how their environments evolve over time. On the other end of the spectrum, we've discovered super-Earths, which are planets that are larger than Earth but smaller than Neptune. These worlds have rocky surfaces and may resemble Earth in some ways, but their larger size and potentially different atmospheres make them distinct. Super-Earths often exist in the habitable zone of their stars, the region where conditions could support liquid water. However, their larger size also means that they may have stronger gravity, potentially altering the kind of life they could support should it exist. One famous super-Earth is Kepler 62f, which is about 1.4 times the size of Earth and lies within the habitable zone of its star. This discovery opened up the possibility that planets with conditions suitable for life could be much more common than we once thought, potentially increasing the chances of finding life elsewhere in the universe. The variety doesn't stop there. Another fascinating category of exoplanets are water worlds, planets that may be completely covered in deep oceans. These worlds are believed to have abundant water on their surfaces, and while they may seem like a paradise for life as we know it, there are challenges. The oceans on these planets could be so vast and deep that the planet's atmosphere might be completely different from anything we've encountered on Earth. Water worlds may not have land masses or the kind of atmosphere needed to sustain life as we understand it, but they offer an exciting avenue for speculation. Could life arise in the depths of these oceans, or could the environment be so extreme that life is impossible? Water worlds challenge our ideas of habitability and push the boundaries of what we consider a life-sustaining environment. But exoplanets aren't just limited to those that orbit stars. There's another, more mysterious class of planets: rogue planets. These are planets that don't orbit any star at all. They drift freely through space, unbound by the gravitational pull of a parent star. Rogue planets could form around a star and later be ejected due to gravitational interactions, or they might form in interstellar space. These planets are harder to detect, as they don't have the brightness of a nearby star to reflect their existence. Yet, they're still out there, silently drifting through the galaxy, raising new questions about how planets can exist without a host star and whether they could still harbour life in some form. As we learn more about these diverse types of exoplanets, we also begin to understand more about the processes that shape planetary systems. Jocelyn Bell Burnell, a pioneering astronomer, helped expand our view of the universe with her discovery of pulsars in 1967. While her discovery wasn't directly related to exoplanets, it opened the door to understanding the vast variety of astrophysical environments in which planets could form. Pulsars are the remnants of massive stars that have exploded in supernovae, and their intense magnetic fields and rapid rotation provide clues about how matter behaves under extreme conditions. The study of these extreme environments helped scientists consider how planets might exist around even the most unusual stars, such as neutron stars and black holes, adding to the growing diversity of planetary environments. One of the most fascinating concepts to emerge from the study of exoplanets is the idea of Tatooine planets. This term is inspired by the iconic Tatooine, the desert planet in Star Wars, which famously orbits two suns. In the real world, there are exoplanets that orbit binary star systems, where two stars serve as the planet's primary sources of light and heat. One of the most famous examples of such a planet is Kepler-16b, discovered in 2011. Kepler-16b orbits two stars just like Tatooine, and it lies about 530 light-years away from Earth. The discovery of planets in binary star systems is particularly exciting because it shows that planets can exist in much more complex environments than we once thought possible. While Tatooine might remain a fictional world, real-life Tatooine-like planets challenge our assumptions about what planetary systems can look like. These discoveries about the variety of exoplanets have not only broadened our understanding of how planets form and evolve, but they've also raised important questions about the potential for life on these planets. Could life exist on a hot Jupiter with scorching temperatures and no solid surface? Could it thrive on a super-Earth, or would the gravity be too overwhelming for life to develop? What about a water world, where the entire planet is covered in ocean? Could life find a way to exist in those vast, endless seas? And what about rogue planets? If they have subsurface oceans or internal heat sources, could they provide a home for life, even though they're drifting through space without a star? The search for habitability is at the heart of many exoplanet discoveries. For years, scientists have focused on finding planets that could support liquid water, because as we know, water is a fundamental ingredient for life as we understand it. But as we discover more about the diversity of exoplanets, it's becoming clear that habitability is more complex than simply finding the right distance from a star. A planet's atmosphere, its chemical composition, and even its magnetic field all play a role in determining whether life can thrive there. It's possible that planets we once thought were inhospitable could in fact support some form of life, and planets we once thought to be ideal candidates for life might turn out to be unsuitable after all. Each new discovery of an exoplanet brings us closer to understanding the full range of possibilities for life in the universe. We've only just begun to scratch the surface of the diversity that exists out there. As our technology improves and our understanding of planetary systems deepens, we'll continue to find more and more types of exoplanets, each with its own unique characteristics and challenges. These discoveries are reshaping our ideas about what makes a planet habitable and what conditions are necessary for life to emerge. And perhaps one day we'll find the answer to one of humanity's most profound questions. Are we alone in the universe? When we think about the possibility of life on other planets, the question we inevitably ask is, could conditions on those planets support life? For much of history, we've assumed that life could only exist in environments similar to Earth's, where liquid water is abundant, temperatures are moderate, and a stable atmosphere exists. But as we discover more about exoplanets, we realize that life could exist in many forms and under conditions vastly different from our own. Two of the most influential theories in the search for extraterrestrial life are Peter Ward and Donald Brownlee's rare earth hypothesis and James Lovelock's Gaia hypothesis. These ideas represent contrasting views on how likely it is that life exists elsewhere in the universe. The rare earth hypothesis, proposed by Ward and Brownlee in 2000, argues that the conditions required for life on Earth are incredibly rare in the universe. According to this hypothesis, Earth's combination of factors, its position in the habitable zone of the Sun, its stable climate, its large moon that stabilizes its axial tilt, its strong magnetic field, and its protective atmosphere, are all extraordinarily unlikely to occur elsewhere. Ward and Brownlee suggest that while the universe is vast and filled with planets, very few of them will have the right conditions to support complex life. In other words, Earth might be the exception rather than the rule, and life as we know it could be an incredibly rare phenomenon in the cosmos. This theory stands in stark contrast to the Gaia hypothesis, proposed by British scientist James Lovelock in the 1970s. Lovelock's theory suggests that life is not just something that exists in response to environmental conditions, but is a force that can actively shape those conditions. According to the Gaia hypothesis, life, whether microbial, plant or animal, can regulate and stabilize a planet's atmosphere and climate, making it conducive to life. This theory proposes that Earth's ecosystems are not passive, but rather act as a self-regulating system that maintains conditions suitable for life. Lovelock's view is more optimistic than the rare Earth hypothesis, suggesting that once life begins to emerge, it might have the ability to alter its environment in such a way that it can survive and thrive. If this theory holds, it could mean that life might be able to exist in more diverse environments than we initially thought, as life could adapt to, and even influence, its surroundings to support its existence. The discovery of exoplanets has allowed scientists to test both of these theories. We now know that planets exist in a wide variety of environments, some of which may be hostile to life as we know it, while others may be more Earth-like than we ever imagined. But how do we determine whether these planets could support life, and what do we look for to know if life exists, or could exist on a distant exoplanet? One of the most promising tools for answering these questions is the study of exoplanet atmospheres. Sarah Seeger, a leading astrophysicist at the Massachusetts Institute of Technology, has played a central role in developing methods for analyzing the atmospheres of exoplanets. Seeger's work focuses on identifying biosignatures, which are chemical signs that might indicate the presence of life. For example, on Earth, the presence of oxygen and methane in the atmosphere is a clear indication that biological processes are occurring. These gases are produced by living organisms, and their presence in a planet's atmosphere could be a telltale sign that life is present, or at least that the planet has conditions that could support life. The study of exoplanet atmospheres has become an essential part of the search for life. Using instruments like the James Webb Space Telescope, set to launch in the near future, scientists will be able to peer deep into the atmospheres of exoplanets and analyze their chemical composition. The ability to detect gases like oxygen, methane, carbon dioxide, and even water vapor will give scientists a clearer picture of the conditions on these planets. A planet with an atmosphere rich in oxygen, for example, could be a strong candidate for further study, as this gas is typically produced by living organisms on Earth. Of course, we must also consider the possibility of false positives. There could be non-biological processes that create these gases too, but the detection of biosignatures would be a major step in the search for extraterrestrial life. While the Gaia hypothesis and biosignatures focus on the more traditional concept of life, there are other theories that challenge our preconceptions about where life might arise. One such theory comes from Thomas Gold, a scientist who proposed the idea that life could originate deep inside planets, far from the surface and the conditions we typically associate with life. In his deep hot biosphere theory, Gold suggested that life could exist in the extreme conditions of a planet's interior, where high temperatures and pressure might create environments conducive to life that we don't yet fully understand. According to Gold, the deep interior of planets might host a type of life that's very different from the life we know, one that thrives on chemical reactions that are not possible at the surface. This idea radically shifts our thinking, as it suggests that life could exist in places we once thought were uninhabitable, places with no sunlight, no surface water, and extreme conditions. This theory opens up new possibilities for where we might find life beyond Earth. For example, some scientists are now considering icy moons, like Europa, one of Jupiter's moons, as potential places where life could exist beneath the surface. These moons have oceans of liquid water beneath thick layers of ice, and the conditions may be right for life to thrive, even without sunlight. In this sense, Gold's theory adds a new layer of complexity to our search for life. suggesting that we might need to look deeper into planets and moons, not just their surfaces, to find signs of life. As we look at all these different theories and ideas, it's clear that the search for life on exoplanets isn't just about finding Earth-like conditions. It's about expanding our definition of what constitutes a habitable environment and considering the possibility that life could exist in ways we haven't yet imagined. From the rare Earth hypothesis, which suggests that Earth's conditions are exceedingly rare, to the Gaia hypothesis, which proposes that life can regulate and sustain its environment, to Thomas Gould's idea that life might thrive deep inside planets, the potential for life in the universe seems to be more diverse and complex than we originally thought. The question of whether we are alone in the universe is one that has fascinated humanity for centuries. As we continue to study exoplanets, we move closer to answering that question, whether life exists on an exoplanet like Earth, or in the extreme environments proposed by Thomas Gould. The search for life beyond our solar system challenges us to think more broadly about the conditions required for life. It encourages us to explore new and unexpected places for life, and to consider that the universe might be teeming with life in forms that are vastly different from anything we've ever imagined. As we continue our exploration of exoplanets, we are not just searching for life, we are redefining what life means and what conditions are necessary for it to exist. The answers we find may reshape our understanding of the cosmos and our place within it. The universe is vast, and as we've learned, it is also teeming with planets. Some of these planets exist in the habitable zone, where conditions might be just right for life to develop, much like Earth. With billions of stars in our galaxy alone, many of them likely hosting planets in these habitable zones, the question arises, if life is so likely, why haven't we detected extraterrestrial civilizations? This question lies at the heart of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for or contact with such civilizations. The Fermi paradox is named after Enrico Fermi, the Italian physicist who, while conversing with colleagues in the 1950s, famously asked, "Where is everybody?" This seemingly simple question encapsulates a complex mystery. Given the sheer number of potentially habitable planets in the universe, especially in our own Milky Way galaxy, it's baffling that we haven't found any concrete evidence of extraterrestrial civilizations. If intelligent life is so common, why haven't we heard from anyone? Or more dramatically, why haven't we even seen signs of other advanced technologies? This paradox has led to many theories and possible explanations, some more speculative than others. One such theory is the uplift hypothesis, proposed by science fiction writer and futurist David Brin. The uplift hypothesis suggests that advanced civilizations might be helping less developed civilizations reach the technological stage needed for interstellar communication and space travel. According to Brin, more advanced species might be out there, but they could be quietly guiding and nurturing emerging civilizations, like humanity, until we're ready to take our place in the greater galactic community. In this scenario, we might not have heard from other civilizations because they're waiting for us to grow up and prove that we can handle the responsibility of interacting with them. Perhaps we're in the process of being uplifted, slowly introduced to the idea of a broader interstellar community. This idea, while speculative, reflects a hopeful view of the universe, suggesting that advanced civilizations might not just be out there, but they might also be watching over us in a sense. Perhaps they are waiting for us to develop the tools, knowledge, and maturity needed to engage with them. It's a theory that challenges our expectations of spacefaring societies as being distant and indifferent, and instead paints them as nurturing mentors. Another explanation for the silence of the cosmos comes from Eugene Parker, a pioneering astrophysicist best known for his theory of the solar wind. Parker proposed that the constant outflow of charged particles from stars could have a significant impact on nearby planets. This idea of space weather has had profound implications, particularly when it comes to understanding how stars, and by extension, entire solar systems, influence their environments. According to Parker, the solar wind and other forms of space weather could strip away the atmospheres of planets, especially those in the early stages of their formation. For planets within the habitable zone of stars, this could be a significant challenge for developing and maintaining life. If a planet is subjected to intense radiation or powerful solar winds, it could become inhospitable long before life has a chance to form. In this context, it's possible that many exoplanets that might be capable of supporting life simply don't have the stable conditions necessary for life to thrive. Moreover, stars themselves are not all the same. Some are much more active than others, emitting intense flares and radiation that could interfere with the development of life. The nature of space weather may explain why some stars with planets that seem to lie in the habitable zone still fail to harbour life. It could be that the conditions for life, although possible, are much rarer than we think, further compounding the mystery of the Fermi paradox. These ideas tie into the work of SETI, the search for extraterrestrial intelligence. SETI is a scientific effort to detect signs of intelligent alien life, usually by scanning the cosmos for radio signals or other forms of communication. For decades, SETI scientists have been scanning the skies, hoping to detect any signals from extraterrestrial civilizations. However, despite decades of searching, they have found nothing definitive. Part of the problem lies in the methods used by SETI. Historically, the organization focused primarily on searching for signals in the radio frequency range. But as our understanding of exoplanets has evolved, so too has the way we think about detecting extraterrestrial life. The discovery of exoplanets, especially Earth-like ones, has shifted the focus from simply searching for radio signals to a broader strategy of studying the atmospheres of distant worlds. With new methods, such as analyzing the light from an exoplanet as it passes in front of its star, SETI's approach is evolving. Scientists are now considering the possibility that advanced civilizations might not use radio waves to communicate at all. Instead, they may be using optical or infrared communications, or even technologies that are beyond our current comprehension. The discovery of biosignatures, chemical compounds that could be associated with life, has become a major part of SETI's new strategy, as scientists look to the atmospheres of exoplanets for signs of life-supporting environments. As technology advances, our methods of listening to the universe are becoming more sophisticated, and the search for extraterrestrial life is becoming more focused. The idea that intelligent life might exist but is simply difficult to detect isn't new. One popular theory is that extraterrestrial civilizations may be deliberately choosing not to communicate with us. This idea, called the zoo hypothesis, suggests that advanced civilizations are aware of humanity, but are deliberately avoiding contact, much like we might avoid interfering with the natural development of animals in a zoo. Perhaps the universe is full of life, but the civilizations we might wish to communicate with are simply taking a wait-and-see approach, not yet ready to make their presence known. This could align with Brin's uplift hypothesis, where intelligent civilizations are waiting for us to reach a certain level of technological and social development before interacting. Alternatively, it is also possible that we are just not asking the right questions. Perhaps the signals or the kinds of life we're seeking are not in the forms we expect, and instead of searching for traditional signs of intelligent life, we need to broaden our definitions and open our minds to the idea that intelligence and communication could take forms we have not yet conceived. As we continue to explore the universe, the Fermi paradox will likely remain one of the great mysteries. But every exoplanet discovered and every new method of detecting life brings us one step closer to finding an answer. Whether the universe is teeming with intelligent civilizations, or whether we are truly alone in the cosmos, the search for extraterrestrial life has the power to reshape our understanding of the universe and our place in it. In the end, the Fermi paradox isn't just a question about extraterrestrial life. It's a question that forces us to think more deeply about our own existence. If we can't find other civilizations, what does that say about our place in the universe? And if we do find life elsewhere, what does that mean for the future of humanity? These are questions that may take years, decades, or even centuries to answer, but they are questions worth asking as we continue our journey into the unknown. The future of exoplanet exploration is incredibly exciting, as new technologies and missions promise to deepen our understanding of distant worlds in ways we never thought possible. For decades, scientists have been studying exoplanets primarily by observing the stars they orbit and detecting subtle signs like the dimming of light as a planet passes in front. However, these methods only scratch the surface of what we can learn. As our capabilities improve, we are now preparing for missions and technologies that will provide a much clearer and more detailed picture of these distant worlds. One of the most exciting upcoming missions is LUVOIR, which stands for the Large UV/Optical/Infrared Surveyor. This proposed space telescope is designed to observe a wide range of wavelengths, from ultraviolet to infrared, allowing scientists to study exoplanet atmospheres in extraordinary detail. LUVOIR is being developed by NASA and is expected to have the ability to directly image exoplanets, providing us with a clearer view of their size, atmosphere, and even surface features. What makes LUVOIR truly special is its ability to directly observe planets in the habitable zone of stars, where liquid water could exist, and potentially even detect signs of life. The telescope would also be capable of studying the atmospheric compositions of these planets, looking for chemical markers that could suggest the presence of life, such as oxygen, methane, and carbon dioxide. LUVOIR's potential to reveal so much about exoplanets is immense. For instance, its ability to study the atmospheres of Earth-like exoplanets will help us understand whether they could support life and what the conditions might be like on these planets. By observing planets around stars much like our Sun, LUVOIR will provide a glimpse into the processes that lead to the formation of habitable worlds and help us understand the factors that influence the development of life. Another important mission in the pipeline is Ariel, the atmospheric remote sensing infrared exoplanet large survey mission. Set to launch in the late 2020s, Ariel will focus specifically on studying the atmospheres of a large number of exoplanets. Unlike LUVOIR, which will provide detailed images of specific planets, Ariel will gather data on a broad range of exoplanets, including both gas giants and rocky worlds. By analysing the chemical composition of these planets' atmospheres, Ariel will help us learn more about the diversity of planets in the universe and how different environmental factors such as atmospheric pressure and temperature influence their ability to support life. One of Ariel's key goals is to study planets that are located in the habitable zone of their stars, those areas where conditions could allow liquid water to exist. The data collected by Ariel will help refine our understanding of the potential habitability of these planets, providing critical information for future missions and our search for signs of life beyond Earth. While space telescopes like LUVOIR and Ariel are pushing the boundaries of what we can learn about exoplanets, other groundbreaking technologies are also playing a vital role in our exploration of distant worlds. One of these technologies is being developed by Roger Angel, a physicist and astronomer known for his work on large-scale space telescopes. Angel's designs focus on creating telescopes capable of directly imaging exoplanets, which would allow scientists to observe them in unprecedented detail. One of Angel's most exciting ideas involves using giant segmented mirrors, potentially the size of entire cities, to create telescopes that can capture images of planets light years away with extreme precision. These large-scale telescopes would provide the resolution needed to study not just the atmosphere, but also surface features of exoplanets. This would be a huge leap forward in our ability to understand their geology, weather, and even the potential for life to exist on their surfaces. Angel's work is part of a larger effort to create next-generation space observatories, which could fundamentally change how we explore exoplanets. These telescopes could not only help us detect exoplanets, but also allow us to study their environments in much greater detail. They could potentially reveal the conditions on these planets, their temperatures, atmospheric compositions, and whether they have oceans, deserts, or polar ice caps. With such powerful instruments, we may soon be able to answer questions that were once purely speculative, like whether other planets have seasons, or how their weather patterns compare to those on Earth. As the technology to observe exoplanets advances, so too does our understanding of the different ways in which planets can exist. Matthew Burley, an astronomer known for his work on planetary atmospheres, is exploring the use of new technologies that will allow us to detect even more exoplanets and study them with greater accuracy. Burley's research focuses on the light that passes through the atmospheres of exoplanets as they transit in front of their stars. By analysing this light, scientists can determine the chemical makeup of a planet's atmosphere, potentially detecting biosignatures that indicate the presence of life. Burley's work is helping to push the boundaries of exoplanetary research, allowing us to identify planets that might be worth investigating further in the search for extraterrestrial life. These advancements in space telescopes and detection techniques are paving the way for even more ambitious projects, such as the idea of interstellar probes. These are spacecraft designed to travel beyond our solar system and explore planets in other star systems. One of the most exciting interstellar missions currently in development is Breakthrough Starshot, an initiative that aims to send small, lightweight probes to the nearest star system, Alpha Centauri, within the next few decades. Breakthrough Starshot proposes to use powerful lasers to propel tiny spacecraft, or starships, to speeds that could allow them to reach Alpha Centauri in just over 20 years. While these probes would be too small to carry detailed scientific equipment, they could gather valuable data on the star system's planets and their potential for habitability. Interstellar probes like Breakthrough Starshot could revolutionize our understanding of exoplanets. By sending probes directly to other star systems, we could gather real-time data about distant planets and their environments. Such missions would provide an entirely new level of detail about exoplanets, offering insights that could not be obtained through telescopes alone. These probes might even one day provide us with the first close-up images of planets in other star systems, allowing us to study their surfaces, weather patterns, and atmospheres in ways we never thought possible. The future of exoplanet exploration is incredibly bright, with an array of upcoming missions and technologies that will vastly expand our understanding of distant worlds. From advanced space telescopes like LUVOIR and Ariel, to large-scale telescopes developed by Roger Angel and interstellar probes like Breakthrough Starshot, we are on the brink of a new era in exoplanetary science. These innovations are set to uncover new insights into exoplanet atmospheres, their potential for habitability, and even the possibility of life beyond Earth. As we continue to push the boundaries of space exploration, we will soon have the tools to study exoplanets with unparalleled precision, unlocking the mysteries of these distant worlds and bringing us closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? The idea of travelling to exoplanets, planets orbiting stars far beyond our solar system, has long been a subject of science fiction. For decades, the idea of interstellar travel seemed like an impossible dream. The vast distances between stars, the limitations of our current technology, and the sheer scale of the challenge made it seem as though humanity would be confined to our own small corner of the universe forever. But as our understanding of space exploration grows and our technological capabilities advance, the possibility of interstellar travel is beginning to move from the realm of fantasy to something that could one day be within our reach. One of the most exciting developments in the field of interstellar exploration is the idea of nuclear propulsion. Traditional rockets rely on chemical propulsion, which works by expelling fuel to produce thrust. While this method is effective for travel within our solar system, it's not nearly fast enough to reach even the nearest stars. To get to an exoplanet, we would need to travel at a significant fraction of the speed of light, which would require a completely different approach to propulsion. Nuclear propulsion offers a potential solution. The concept involves using nuclear reactions, either nuclear fission or nuclear fusion, to generate thrust. Nuclear fission, which is the process of splitting atoms to release energy, has already been used in space missions, such as in some of the spacecraft that powered long-duration missions like Voyager and Parker Solar Probe. These spacecraft have shown that nuclear power can provide a long-lasting source of energy, but the type of propulsion needed for interstellar travel would need to be far more powerful. The idea of nuclear fusion, which involves fusing atomic nuclei to release energy, holds even more promise for interstellar travel. Fusion is the process that powers the sun, and if we can harness it on Earth, it could provide an almost limitless source of energy. Fusion-powered spacecraft could potentially achieve speeds far greater than anything possible with chemical rockets. While nuclear fusion has not yet been fully realized on Earth, scientists and engineers are making significant strides toward mastering this technology. If we can develop fusion propulsion, we could one day send spacecraft to distant exoplanets at speeds that would make interstellar travel feasible. Another promising concept for interstellar travel involves light sails. Light sails are thin, reflective surfaces that can be propelled by the pressure of light. When light particles, or photons, hit the surface of a light sail, they transfer momentum, causing the sail to move. This concept may sound too simple to be effective, but the physics behind it is sound. In theory, light sails could be propelled by powerful lasers or even the sun's light, potentially allowing spacecraft to reach speeds approaching a significant fraction of the speed of light. One of the most notable projects in this area is Breakthrough Starshot, an ambitious initiative that aims to send tiny, lightweight probes to the nearest star system, Alpha Centauri, in just a few decades. These probes, known as starships, would be propelled by powerful laser beams that would push them to speeds of up to 20% of the speed of light. While the technology is still in the early stages, the idea of sending probes to another star system within a human lifetime represents a giant leap forward in our ability to explore distant exoplanets. These probes would be small, carrying limited scientific equipment, but they could gather vital data about the star system, providing valuable insights into the conditions on exoplanets like Proxima Centauri b, a planet in the habitable zone of Alpha Centauri. But even with the promising technologies of nuclear propulsion and light sails, there are still enormous challenges to overcome before interstellar travel becomes a reality. The vast distances between stars are a major obstacle. Even the closest star system to us, Alpha Centauri, is more than 4 light-years away. That means that even travelling at the speed of light, it would take over 4 years to reach it. With current spacecraft, the journey would take tens of thousands of years, far beyond the lifespan of any spacecraft or crew. To make interstellar travel feasible, we would need to develop propulsion systems that can travel at a significant fraction of the speed of light, or perhaps find ways to make use of advanced concepts like warp drives or wormholes, though these ideas are still theoretical. Another significant challenge is the issue of energy. Even a spacecraft travelling at a fraction of the speed of light would need an immense amount of energy to overcome the gravitational pull of its home star and maintain its speed over the course of such a long journey. Nuclear fusion, or matter-antimatter reactions, could provide the necessary energy, but these technologies are still in the experimental stage. Beyond propulsion and energy, there are other challenges that must be addressed before interstellar travel becomes possible. One of the most pressing concerns is the protection of spacecraft from the hazards of space, such as cosmic radiation and micrometeoroids. Travelling at a significant fraction of the speed of light would also raise concerns about interstellar dust, which, at such speeds, could cause severe damage to spacecraft. The effects of prolonged space travel on human health would also need to be understood, as radiation exposure, the psychological challenges of isolation, and the effects of microgravity could have significant impacts on any crewed mission. Yet despite these challenges, private companies like SpaceX are pushing the boundaries of space exploration in ways that were once unimaginable. SpaceX, founded by Elon Musk, has made significant advancements in rocket technology with the development of the Falcon Heavy and Starship rockets. These rockets have the potential to revolutionize space travel, making it cheaper and more efficient to send payloads to space. Musk's long-term goal is to make human life multiplanetary, with Mars as the first target. The advancements made by private companies like SpaceX are laying the groundwork for future space exploration, and some of these breakthroughs could eventually play a role in the journey to the stars. While SpaceX's focus is on near-term goals like sending humans to Mars, the company's success in reducing the cost of space travel could make interstellar exploration more achievable in the long term. If we can develop the infrastructure to support missions to Mars and beyond, it might be easier to tackle the even greater challenge of sending missions to exoplanets. All of these efforts are ultimately part of a larger question. What is humanity's place in the universe? As we push the boundaries of space exploration and develop new technologies, we are not just preparing for the next great adventure. We are asking fundamental questions about the nature of life, the limits of human ingenuity, and the future of our species. The search for exoplanets and the possibility of interstellar travel are not just about discovering new worlds, they're about understanding our place in the cosmos. The future of space exploration is bound to be filled with extraordinary challenges and incredible opportunities, and with every step we take, we get closer to answering some of the universe's most profound questions. Interstellar travel may still seem like a far-off dream, but with each breakthrough in technology, we move closer to a future where the stars are within our reach. And perhaps, just as importantly, this pursuit is not just about discovering new planets. It's about discovering who we are and where we fit into the grand tapestry of the universe. The discovery of exoplanets, planets that orbit stars beyond our solar system, has not only expanded our knowledge of the cosmos, but also raised deep philosophical questions about our place in the universe. For centuries, humans have looked up at the stars and wondered if we are truly alone, or if there are other worlds out there that might host life. With the discovery of thousands of exoplanets, some of which appear to be in the habitable zone where conditions might support liquid water, the question of whether we are alone in the universe has become more pressing than ever. As we continue to discover more about these distant worlds, we must confront not just scientific questions, but also the philosophical implications of these findings. One of the most profound philosophical ideas raised by the discovery of exoplanets is the possibility that life exists elsewhere in the universe. If life can form and thrive on Earth, why should Earth be the only place where life exists? The sheer number of potentially habitable planets suggests that life might be a natural outcome of certain conditions. This raises the question, if there is life elsewhere, what does that mean for our understanding of ourselves and our place in the cosmos? Are we truly unique, or are we just one example of a more widespread phenomenon? One theory that challenges the idea of a universe full of life is the simulation hypothesis, proposed by philosopher Nick Bostrom. This hypothesis suggests that the universe, as we know it, could be a simulation, a kind of artificial reality created by a more advanced civilization. According to Bostrom, if we were to ever develop advanced enough technology, it might be possible to create simulations of entire worlds, including intelligent beings. This raises an intriguing possibility. Could our entire universe be a simulation? And if it is, what does that mean for the search for life beyond Earth? Bostrom's theory posits that an advanced civilization might simulate the experiences of beings like us, and perhaps even the conditions for life. If that's the case, then the discovery of exoplanets and the search for extraterrestrial life might be part of that larger simulated reality. Perhaps these discoveries are part of the game, so to speak, a simulation designed to explore the possibility of life elsewhere in the universe, but within the controlled environment of a simulation. While the simulation hypothesis is still speculative and raises more questions than answers, it also serves as a reminder that our understanding of reality is constantly evolving. The more we learn about exoplanets, the more we realize that the universe is far stranger and more complex than we ever imagined. Whether we're looking for life on distant worlds or contemplating the nature of our own existence, exoplanet discoveries challenge us to think deeply about the very nature of reality itself. This challenge to our understanding of the universe is echoed by the words of Carl Sagan, the famed astronomer and science communicator, who famously said, "We are made of star stuff." Sagan's words encapsulate the idea that everything on Earth, including us, is ultimately derived from the elements formed in the cores of stars. The very atoms that make up our bodies were once forged in the intense heat of a star, and when those stars exploded in supernovae, they scattered these elements across the universe, allowing new stars and planets to form. In this sense, Sagan's quote connects us not just to the Earth, but to the entire universe. We are part of a grand cosmic cycle, constantly evolving and being reshaped by the forces of nature. Sagan's quote also reminds us of the interconnectedness of all things. As we discover more exoplanets, we are forced to confront our own place in this vast universe. If we are made of star stuff, then we are intimately connected to the stars and the planets that orbit them. Each new exoplanet discovered is a reminder that we are part of something much larger than ourselves, a universe filled with countless worlds, each with its own story. The discovery of exoplanets forces us to reconsider our sense of importance in the grand scheme of things. We may be one small species on one small planet in one corner of the universe, but that doesn't mean we are insignificant. Instead, it means that we are part of an ongoing cosmic story, one that stretches back billions of years and will continue long after we are gone. As we explore these distant worlds and search for signs of life, we must also ask ourselves what it means to be human. The discovery of exoplanets challenges us to think beyond our own planet and to consider the possibility that life, intelligence, and civilization might be more widespread than we previously imagined. Are we the only intelligent beings in the universe? Or are we just one among many? If we find life on another exoplanet, how will that change our understanding of ourselves and our place in the universe? The exploration of exoplanets also raises questions about the future of humanity. As we search for signs of life beyond Earth, we are also thinking about our own future in the cosmos. How will we respond to the discovery of extraterrestrial life? Will we find ways to communicate with other civilizations, or will we remain isolated in our own corner of the universe? What if we discover that Earth is the only planet capable of supporting life? How will we address the challenges of preserving life on our own planet, knowing that the universe is filled with potential worlds that might one day support life? The discovery of exoplanets also impacts our future in more practical ways. As we study these distant worlds, we gain insights into the processes that govern the formation of planets and the conditions necessary for life. This knowledge could help us better understand the history of our own planet and the factors that have made Earth hospitable to life. By studying exoplanets, we can learn more about the conditions that could allow humanity to survive in the future, especially as we face challenges like climate change and resource depletion. If we are to become a multi-planetary species, the study of exoplanets could help us identify potential places where humanity could one day thrive, either by terraforming planets or by building new habitats. Ultimately, the study of exoplanets is about more than just exploration. It's about finding meaning in the vastness of the universe. It's about understanding our place in the grand cosmic order and confronting the philosophical questions that arise from our discoveries. As we continue to search for life on distant worlds, we're also searching for answers to the age-old questions of who we are and where we come from. The search for life beyond Earth is not just a scientific endeavour, it is a deeply human quest that touches on our curiosity, our sense of wonder, and our desire to understand the universe and our place within it. In the end, the discovery of exoplanets forces us to confront the enormity of the cosmos and to ask ourselves what it means to be part of it. Whether we are alone in the universe or part of a much larger community of life, the search for exoplanets is a journey that is just beginning, one that will continue to challenge our understanding of life, the universe, and everything in between. As we venture into the unknown, we may just discover not only new worlds, but also new ways of thinking about our own. The formation of planets is one of the most fascinating and complex processes in the universe. It begins in the cold, dark depths of space, where clouds of gas and dust, known as solar nebulae, slowly collapse under their own gravity. This collapse leads to the creation of stars, but it also plays a crucial role in the formation of planets. This process, known as the solar nebula theory, is fundamental to understanding how planets form in both our solar system and in distant exoplanetary systems. In essence, the solar nebula theory tells us that when a star forms, it doesn't do so in isolation. Instead, it forms in a swirling disk of gas and dust. As the central part of this disk contracts, it heats up and becomes the star. Meanwhile, the outer regions of the disk, composed of smaller particles, begin to stick together through a process called accretion, where dust and gas gradually combine to form larger and larger objects. These objects eventually become planetesimals, which are the building blocks of planets. One key aspect of planet formation is how planetesimals come together. John Chambers, an astrophysicist, has made significant contributions to understanding this process, particularly focusing on the way planetesimals collide and stick together in the early stages of planetary formation. Chambers developed models of planetesimal accretion, which showed that when these small objects collide, they often merge, eventually growing large enough to become planets. This process is crucial for understanding how the solid cores of planets like Earth and Mars form, and how they gain the mass and structure necessary to attract atmospheres and support the conditions needed for life. The work of Chambers and others has also helped us understand that not all planets form in the same way. For example, many exoplanets are found in binary or trinary star systems, where 2 or 3 stars orbit each other. This adds a level of complexity to the formation process, as the gravitational forces from multiple stars can alter the orbits of planetesimals and the planets themselves. For example, a planet in a binary star system may experience 2 different sources of light and heat, making its environment radically different from a planet that orbits a single star. The research of Elena L. Adams, an astrophysicist who studies planetary formation in multi-star systems, has shed light on how planets form in these unique environments. Adams' work suggests that while the presence of multiple stars can complicate the process, it also opens up new possibilities for planet formation. For instance, in some binary or trinary systems, planets can form in stable orbits that allow for the accumulation of material in much the same way they would in a single star system. However, in more chaotic environments, planets may be flung out of their orbits or may collide with other bodies, leading to dramatic changes in their structure and potential for habitability. This concept of planetary formation in multi-star systems is particularly important when we consider the possibility of habitable exoplanets in these systems. A planet in a binary system, for example, may experience more extreme seasons or unusual weather patterns, making it harder to support life as we know it. However, it's also possible that life could adapt to these different conditions, leading to the emergence of ecosystems that are radically different from those on Earth. The role of gas giants in planetary formation is another key piece of the puzzle. Gas giants like Jupiter and Saturn are typically found in the outer regions of a planetary system, far from their host star. However, their influence on the rest of the system can be profound. Gas giants are not just massive planets. They are dynamic, gravitationally influential bodies that can alter the orbits of other planets and planetesimals within the system. In some cases, gas giants can even prevent the formation of planets in the inner regions of the system. This phenomenon, known as orbital migration, occurs when a gas giant moves inward toward its star, clearing out the space between it and the inner planets, which can leave behind a system dominated by smaller rocky worlds like Earth. But gas giants don't just have a negative impact on the inner planets. They can also play a role in shaping the structure of a planetary system in ways that are beneficial for life. For example, Jupiter's gravitational influence in our solar system has helped protect the Earth from potential collisions with asteroids and comets, acting as a kind of cosmic shield. In exoplanetary systems, the presence of gas giants may similarly protect rocky planets from dangerous impacts, while also helping to maintain the stability of their orbits. This makes gas giants essential to the long-term stability of planetary systems and may increase the chances of habitability on nearby rocky planets. As we continue to explore exoplanets, one of the most important aspects of their study is their atmospheres. The composition and structure of an exoplanet's atmosphere can provide vital clues about its potential for habitability. Planets with thick atmospheres may trap heat, leading to a greenhouse effect that could make them too hot for life to thrive. Conversely, planets with thin or absent atmospheres may be too cold for liquid water to exist. Understanding the relationship between exoplanetary atmospheres and their ability to support life is one of the key goals of future exoplanet research. The study of planetary atmospheres is also crucial for understanding the potential for life on other worlds. Sarah Seeger, a leading researcher in the study of exoplanet atmospheres, has developed innovative techniques for analyzing the light that passes through a planet's atmosphere as it transits in front of its star. By studying how the light changes, scientists can determine the composition of the atmosphere, including the presence of gases like oxygen, methane, and carbon dioxide, key indicators that life may exist or could have once existed on a planet. These techniques, along with advances in space-based telescopes like LUVOIR and Ariel, are helping to unlock the secrets of exoplanetary atmospheres and provide new insights into the potential for life beyond Earth. The study of exoplanetary atmospheres is not just about searching for signs of life, it's also about understanding the processes that shape the evolution of planets. The composition of a planet's atmosphere can reveal much about its history, from the gases that were present when the planet first formed to the changes that have occurred as a result of volcanic activity, atmospheric escape, or other factors. By studying the atmospheres of exoplanets, we can learn more about the conditions that make a planet habitable and the processes that might make a planet unsuitable for life. As we continue to explore exoplanets and learn more about how they form, it becomes increasingly clear that the search for life in the universe is not just about finding planets that are similar to Earth. It's about understanding the wide range of possibilities that exist in the cosmos and the diverse conditions that might give rise to life. From the formation of planets in multi-star systems to the role of gas giants in stabilizing planetary orbits, the study of exoplanets is transforming our understanding of the universe and our place within it. And as we continue to make new discoveries, we will likely find that the building blocks of life, and the conditions necessary to support it, are more varied and complex than we ever imagined. When we look to the stars and contemplate the possibility of life beyond Earth, one of the most exciting and promising areas of study is the search for biosignatures, chemical signs that might indicate the presence of life. One of the best ways to detect these biosignatures is by studying the atmospheres of exoplanets. Just as Earth's atmosphere contains gases like oxygen and methane, which are tied to biological processes, scientists hope to find similar signs on distant worlds that might suggest life, or the potential for life, exists elsewhere in the universe. The most prominent gases to look for are oxygen, methane, and carbon dioxide. These gases, especially when found in certain combinations, are considered biosignatures because on Earth they are primarily produced by living organisms. For example, oxygen is produced by plants and photosynthetic organisms, while methane is often associated with biological processes in animals and microbes. Carbon dioxide, while a natural part of a planet's atmosphere, also plays a crucial role in regulating the climate, and its presence in the right proportions can tell us much about a planet's overall environmental conditions. To detect these gases, scientists use a technique called spectroscopy, which involves analysing the light that passes through a planet's atmosphere when the planet transits in front of its star. As light passes through the atmosphere, some wavelengths of light are absorbed by the gases in the atmosphere, leaving behind a distinctive pattern in the light that can be analysed by astronomers. By studying these absorption patterns, scientists can determine what gases are present and even measure their concentrations. Mark E. Everett, an expert in atmospheric modelling, has been instrumental in developing methods to assess whether the conditions on exoplanets might support life. Through his work, Everett has created models that simulate how gases like oxygen, methane, and carbon dioxide interact with their planet's atmosphere. These models help scientists predict the likelihood that certain combinations of gases could be a sign of biological activity, rather than just the result of natural processes like volcanic eruptions or atmospheric chemistry. Everett's work is crucial for narrowing down the exoplanets that are worth studying further in the search for life. The discovery of exoplanets with atmospheres that could support life has become a central goal of modern astrophysics. And with the advent of the James Webb Space Telescope, or JWST, we're on the cusp of a new era in our ability to study exoplanet atmospheres. The JWST is set to be the most powerful space telescope ever launched, capable of observing exoplanet atmospheres with unprecedented detail. Unlike its predecessors, which primarily observed visible and ultraviolet light, the JWST will focus on infrared light, allowing it to penetrate the thick clouds of gas and dust that often obscure our view of distant planets. This will allow scientists to study the chemical composition of exoplanet atmospheres in ways that were once unimaginable. The JWST will be able to detect even faint traces of gases like oxygen, methane, and carbon dioxide, helping us identify which exoplanets might have the right conditions for life. By studying the atmosphere of a planet in the habitable zone of its star, where liquid water might exist, astronomers can gather crucial data on the planet's climate, weather patterns, and potential habitability. One of the most exciting aspects of the JWST is its ability to detect biosignatures, gases that are produced by living organisms. In the coming years, it will become a powerful tool for identifying exoplanets that may harbour life. Another scientist who has made significant contributions to our understanding of exoplanet atmospheres is David C. Catling, a researcher at the University of Washington. Catling has studied how different types of planetary atmospheres can support life, looking at both Earth-like atmospheres and more exotic environments. His work has revealed that while Earth's atmosphere is uniquely suited for supporting life, other types of atmospheres, such as those dominated by carbon dioxide or nitrogen, might also be capable of sustaining life, albeit in very different forms. Catling has also explored the potential for life to exist in atmospheres that are very different from Earth's. For example, he has studied the possibility of life thriving in planets with atmospheres that are thick with carbon dioxide, a greenhouse gas that could trap heat and create a warm, stable environment. While such conditions might not be conducive to life as we know it, they could still support different forms of life, potentially thriving in environments much hotter or more acidic than Earth's. One particularly interesting concept that has emerged from Catling's work is the idea that life could exist in subsurface oceans, similar to those found on some of the moons of our own solar system. For example, Europa, one of Jupiter's moons, is thought to have a vast ocean of liquid water beneath its icy surface. Similarly, Enceladus, a moon of Saturn, has been shown to expel water vapor and organic compounds into space, hinting at the possibility of a hidden ocean beneath its icy crust. Catling's research suggests that exoplanets with thick atmospheres could have similar environments, where life could take root deep beneath the surface, sheltered from the harsh conditions of the planet's exterior. As we continue to study the atmospheres of exoplanets, we're beginning to realize just how diverse the conditions for life can be. While we've focused much of our search on planets that resemble Earth, we're starting to consider a wider range of environments where life might thrive. Some planets may have atmospheres rich in methane and hydrogen, while others might have thick carbon dioxide clouds that create a runaway greenhouse effect. In some cases, life could exist in subterranean oceans, protected from the extreme conditions above. The more we learn about the diversity of planetary atmospheres, the more we realize that the possibilities for life beyond Earth are far more varied than we once thought. With future missions and instruments like the James Webb Space Telescope and Ariel, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, we are poised to take the next big step in the search for life on exoplanets. As we analyze the chemical signatures of distant worlds, we may one day discover biosignatures that point to the existence of life on a distant exoplanet, perhaps in ways we haven't even imagined yet. And while the possibility of finding life on another planet is thrilling, it's also a reminder that the universe is vast and full of mysteries, waiting to be uncovered. As our ability to detect and study exoplanet atmospheres grows, so too does our understanding of what makes a planet habitable, and how life might arise in the most unexpected of places. With the tools and technologies we have today, and those on the horizon, we are on the cusp of a new era in astrobiology. The search for life beyond Earth is no longer just a matter of looking for familiar signs of life, but of expanding our understanding of what life can look like and where it can exist. It is an exciting time for science, as we venture deeper into the unknown, exploring the possibilities that lie on distant worlds, waiting to be discovered. As we shift from studying the atmospheres of exoplanets to thinking about how we might one day visit or even settle on these distant worlds, the next big question will be, can we truly become a multi-planetary species? The journey to answer that question begins with understanding the atmospheres of exoplanets and their potential for sustaining life. The concept of colonizing exoplanets has long been the stuff of science fiction, but as our understanding of space exploration grows, the theoretical possibilities are becoming more tangible. The dream of humans living on distant worlds, starting a new chapter for humanity beyond Earth, is something that, while still far off, is being seriously explored. Whether through terraforming human adaptation to alien environments or the creation of artificial habitats, the idea of colonizing exoplanets is no longer just a speculative fantasy. Terraforming is perhaps the most talked about method for making exoplanets more hospitable to humans. The idea is simple in principle. Transform an alien planet's atmosphere and surface to resemble Earth's, creating conditions that can support human life. This could involve altering the composition of the atmosphere, adjusting the temperature, and introducing elements that are necessary for human survival, such as oxygen and water. Of course, terraforming is a complex and highly speculative concept, and many challenges remain in making it a reality. One person who has significantly contributed to the theory of terraforming is Robert Zubrin, a well-known advocate for the colonization of Mars. Zubrin's work on terraforming Mars, in particular, his concept of using greenhouse gases to warm the Martian atmosphere, has provided a blueprint for thinking about how we might make hostile planets more Earth-like. Zubrin suggests that by releasing carbon dioxide into the Martian atmosphere, we could create a runaway greenhouse effect that would gradually warm the planet, potentially making it more habitable. He proposes using resources already present on Mars, such as ice deposits, to produce the necessary gases and chemicals. Although Zubrin's ideas are focused on Mars, the basic principles of terraforming could be applied to other exoplanets as well. However, each exoplanet would present its own unique challenges. For example, if a planet is too far from its star, it might not receive enough sunlight to drive the kind of greenhouse effect needed for terraforming. If the planet is too close, the intense heat could make it impossible to introduce the necessary balance of gases. The specific gravity and atmospheric pressure of an exoplanet would also influence how terraforming would proceed. Some exoplanets may have gravity that is much stronger or weaker than Earth's, which would have profound effects on human physiology and the ability to adapt to the new environment. Another critical aspect of colonizing exoplanets is the need for advanced life support systems. While some exoplanets might have atmospheres that are close to Earth's, many others will not. This is where the work of Ralph L. Lawrence, a researcher in life support systems, becomes particularly relevant. Lawrence has explored the idea of creating artificial environments on exoplanets that could provide the necessary conditions for human life. These closed-loop life support systems would provide oxygen, food, and water, and regulate temperature and waste, all within a controlled environment. Lawrence's work suggests that with the right technology, we could create self-sustaining habitats on exoplanets, allowing humans to live and thrive, even if the planet's natural environment is unsuitable for life. These life support systems would not only have to be resilient, but also adaptable. they would need to support humans in environments with extreme temperatures, different levels of radiation, and perhaps even low or high gravity. To make human colonization of exoplanets feasible, these systems would need to be incredibly advanced, with redundant backups and the capacity to adjust to changing conditions on the planet. Speaking of radiation, the lack of a magnetic field on many exoplanets could pose a significant challenge. Earth's magnetic field protects us from harmful solar radiation, but many exoplanets, especially those orbiting stars more active than our Sun, may not have this natural protection. Without a magnetic field, the radiation from the star could strip away a planet's atmosphere or make it impossible for life to survive on the surface. To address this, future colonization efforts might involve building radiation-shielded habitats or utilizing underground structures to protect settlers from radiation exposure. Gravity is another obstacle. While the idea of colonizing exoplanets with gravity similar to Earth's is appealing, many exoplanets will have different levels of gravity. For instance, if a planet has gravity much stronger than Earth's, it could lead to health issues for humans, such as difficulty moving and an increased risk of cardiovascular problems. On the other hand, if the gravity is too weak, it could lead to muscle atrophy and bone density loss over time. Long-term space travel and living on low-gravity planets could force humans to develop new ways of adapting to these conditions, such as specialized exercise regimens or even genetic modifications. But even with all these challenges, the potential for colonizing exoplanets is growing more plausible with each passing year. Private companies, like SpaceX, are already making significant advancements in space exploration with the goal of making human life multiplanetary. SpaceX's Starship, a fully reusable spacecraft designed for deep space travel, could one day serve as a vessel for missions to exoplanets. While the company's current focus is on sending humans to Mars, the technology developed for this mission could be adapted for interstellar travel. The development of advanced space propulsion systems like nuclear fusion or light sails could further revolutionize the possibilities for interstellar travel and colonization. The challenges of traveling to and colonizing exoplanets are immense, but so are the rewards. Successful colonization of exoplanets would not only expand the human footprint in the universe, but also provide humanity with a backup plan in case something were to happen to Earth. It could also offer new opportunities for scientific discovery and exploration, as we study the processes that shape planets and ecosystems beyond our own solar system. In addition to the technical hurdles, there are also ethical considerations regarding the colonization of exoplanets. If we were to discover an exoplanet with conditions that could support life, should we terraform it to make it more Earth-like, or would that amount to a form of cosmic colonialism? And if we did find life, how would we go about interacting with it? These are questions that humanity will need to address as we move closer to the reality of interplanetary and interstellar exploration. Ultimately, the colonization of exoplanets may depend not just on advancements in technology, but also on the collective will and vision of humanity. As we continue to push the boundaries of space exploration, the potential for human expansion into the cosmos is vast. While colonizing exoplanets is still in the realm of theory, the steps we take today, developing new technologies, exploring the feasibility of terraforming, and understanding the nature of life support systems, are laying the groundwork for what could one day be a new chapter in human history. The journey to distant stars may take decades or even centuries, but the foundation for humanity's future in space is already being built, one technological breakthrough at a time. The search for Earth 2.0, a planet that mirrors Earth in its ability to sustain life, has become one of the most compelling and ambitious goals in modern astronomy. With billions of stars in our galaxy alone, many of which likely host planets in the habitable zone, the region where conditions are just right for liquid water to exist, the possibility of finding an exoplanet that closely resembles Earth is tantalizing. But as the search continues, scientists are learning that identifying an Earth-like world is much more complex than simply finding a planet that looks like our own. One of the leading experts in the search for Earth-like exoplanets is Sarah Seeger, a professor of planetary science at the Massachusetts Institute of Technology. Seeger has made significant contributions to the study of atmospheres on exoplanets, particularly in understanding how we can detect conditions that might be suitable for life. Her work focuses on analyzing the chemical makeup of exoplanetary atmospheres, looking for gases like oxygen, methane, and carbon dioxide, which on Earth are closely linked to biological processes. Seeger's research aims to identify which exoplanets might have atmospheres similar to Earth's, and therefore could potentially support life. The key to identifying an Earth 2.0 lies in studying habitable zones, regions around stars where temperatures are conducive to liquid water. The discovery of exoplanets in these zones has led to an explosion of interest in planets that might harbour life. However, the search is not just about finding planets in the right location. It's also about examining the atmospheric conditions and the physical environment of the planet. Just because a planet is in the habitable zone does not mean it will automatically have Earth-like conditions. Factors like atmospheric composition, surface temperature, and the presence of water are all crucial in determining whether a planet could sustain life as we know it. One of the most famous discoveries in the search for Earth-like exoplanets is Proxima Centauri b, a planet located around 4 light-years away in the Proxima Centauri system. This planet orbits within the habitable zone of its star, Proxima Centauri, a red dwarf star. Proxima Centauri b has been hailed as one of the most promising candidates for finding life beyond our solar system. While the discovery is exciting, it also raises numerous questions about the planet's ability to truly support life. Proxima Centauri is a much cooler star than our Sun, and its intense stellar flares may make it difficult for life to survive on the planet's surface. In addition, we still know very little about the planet's atmosphere and whether it could support liquid water, which is essential for life as we know it. Despite the exciting potential of planets like Proxima Centauri b, there are significant challenges in verifying whether an exoplanet truly possesses Earth-like conditions. One of the major obstacles is the lack of direct observations. While astronomers can detect exoplanets using methods like transit photometry and radial velocity, these methods only provide indirect evidence of a planet's existence and don't give us a full picture of its environment. In order to study the atmospheres of exoplanets in detail, we need advanced telescopes and instruments capable of detecting the faint signals of gases and other atmospheric components. The James Webb Space Telescope, JWST, set to launch in the near future, will be a game-changer in this regard. With its powerful infrared capabilities, JWST will be able to study the atmospheres of exoplanets in far greater detail than ever before. By examining the light that passes through a planet's atmosphere as it transits its star, JWST will be able to detect the chemical signatures of gases like oxygen, methane, and carbon dioxide, as well as trace gases that might indicate the presence of life. This will help us answer the critical question: does life exist beyond Earth? JWST's ability to detect and analyze the atmospheres of exoplanets will provide some of the most direct evidence we have of a planet's habitability. However, even with advanced instruments like the JWST, there are still significant uncertainties in our ability to determine whether an exoplanet truly has Earth-like conditions. For example, a planet could have an atmosphere that contains oxygen and methane, but these gases could be produced by non-biological processes, such as volcanic activity or chemical reactions in the planet's atmosphere. To definitively say that life exists or could exist on a planet, we need to find a combination of biosignatures, gases that are produced by living organisms in a stable, self-regulating system, along with other environmental factors such as liquid water and a stable climate. In addition to the search for Earth-like atmospheres, we must also consider the geological and climatic conditions on exoplanets. Earth's habitability is not just a result of its atmosphere, but also the result of the planet's dynamic geology and climate. Plate tectonics, for example, play a crucial role in regulating the planet's temperature and recycling carbon through the carbon silicate cycle, which helps maintain a stable climate over geological timescales. Understanding the geological processes of other planets, including the presence of water and volcanism, will be critical for determining their ability to support life. The search for Earth 2.0 is not just about finding another planet that looks like ours. It's about understanding the complex interplay of factors that make a planet habitable. From the atmosphere and water availability to geological processes and climate stability, every aspect of a planet's environment contributes to its potential for sustaining life. While we have made incredible strides in identifying exoplanets in habitable zones, the true challenge lies in verifying whether these planets actually have the right conditions for life. As we continue to discover more exoplanets, we are also beginning to rethink what it means for a planet to be Earth-like. Life on Earth thrives in a very specific set of conditions, but life elsewhere might not require the same exact conditions. We are learning that the possibilities for habitability are much broader than we initially thought. Planets that are very different from Earth, whether they are hotter, colder, or have a radically different atmosphere, might still be able to support life in forms we can't yet imagine. And even if we don't find life on these distant worlds, studying their conditions will tell us more about the processes that shape planets and life, helping us understand the origins of life on Earth. The discovery of Earth-like exoplanets is more than just an exciting scientific achievement. It challenges our assumptions about the uniqueness of our planet and forces us to ask fundamental questions about the nature of life and our place in the universe. As we continue to search for Earth 2.0, we are not just looking for another planet like ours. We are learning more about ourselves and the possibilities for life in the universe. The discovery of exoplanets has fundamentally reshaped our understanding of the universe and our place within it. For centuries, Earth was considered the center of the cosmos, with humans as the focal point of creation. The idea that planets orbiting distant stars light years away could exist at all was once unimaginable. Yet today, we know that exoplanets are as common as stars themselves, and the possibility that many of these worlds could harbour life, or at least conditions conducive to life, has profound implications for how we view our own existence. Exoplanet discoveries are not just a matter of cataloguing distant worlds. They fit into a much grander narrative, one that begins with the formation of stars and galaxies. The birth of stars and planetary systems starts with the collapse of gas and dust clouds, which over time condense to form stars and the planets that orbit them. This process, known as stellar formation, is not unique to our solar system. Everywhere we look in the universe, stars are forming, and around many of them, planets are being born. The existence of exoplanets is a natural consequence of this process, and the sheer number of exoplanets we've discovered so far suggests that planetary systems are an intrinsic part of the cosmic fabric. One of the most profound voices in modern science, Neil deGrasse Tyson, has frequently highlighted the interconnectedness of all life and matter in the universe. Tyson's perspective emphasizes that, from the smallest particles to the largest structures in space, everything is part of the same grand cosmic dance. According to Tyson, the atoms that make up our bodies, our planet, and everything around us were once formed in the hearts of ancient stars. In a sense, we are literally made of star stuff. This idea underscores the unity of the universe, where every object and every living thing is tied together by the same processes that govern the cosmos. Exoplanets, in this context, are not isolated or distant objects. They are part of the same cosmic network that links all stars, planets, and life forms. The discovery of planets orbiting distant stars serves as a reminder that we are not alone in the universe. While Earth may be unique in many ways, the process that led to the formation of our planet is likely repeating itself across the galaxy, and perhaps even the universe. Just as our planet formed around our star, other planets are forming around other stars, with the potential to support life in ways we are just beginning to understand. The discovery of exoplanets also challenges our concept of uniqueness. For centuries, humanity held a special place in the universe, with Earth regarded as the only cradle of life. The search for extraterrestrial life has always been motivated by the hope that we might find other civilizations, or at the very least, evidence that life can thrive elsewhere. But the discovery of thousands of exoplanets, many of which lie in the habitable zone of their stars, suggests that the conditions for life may not be as rare as we once thought. If life can arise on other worlds, it may be more common than we realize, and Earth may no longer hold the distinction of being the only planet capable of supporting life. This realization has profound philosophical implications. It forces us to rethink our place in the universe. If life can emerge on other planets, then perhaps we're not so unique after all. It opens up the possibility that we're part of a much larger web of life, scattered across the cosmos, and that the process of evolution and the emergence of intelligent beings may not be limited to Earth. This idea has led to a shift in how we think about life and our responsibility to the universe. If we are not alone, what does that mean for humanity's future? How should we interact with other forms of life if we find them? And what does it mean for us to be part of this larger cosmic story? Exoplanet discoveries also force us to reconsider the very concept of home. For centuries, we have viewed Earth as our only home, a place that is uniquely capable of supporting life. But as we discover more and more planets in the habitable zone of distant stars, the notion of home begins to expand. Could we one day consider another planet as our home? The idea of colonizing exoplanets, once relegated to science fiction, is now being seriously considered. As we explore planets that resemble Earth, we are forced to ask whether these worlds could someday become humanity's new home, whether as a place to settle or as a base for further exploration. Yet, even as we look beyond Earth, we must also confront the challenges that come with colonizing other planets. Exoplanets, though they may seem Earth-like, are not guaranteed to be hospitable to human life. Their atmospheres, gravity, and radiation levels may be vastly different from what we're accustomed to. As we search for habitable worlds, we are not just looking for planets that resemble Earth, but also for those that offer the best chance for survival and growth. The discovery of Earth-like exoplanets will require us to rethink what it means to live on another planet and how we can adapt to new environments. The question of whether we are alone in the universe is one that has intrigued humanity for centuries. As we continue to discover exoplanets, we are edging closer to finding an answer. However, the implications of these discoveries go far beyond the search for life. They challenge our understanding of what it means to be human, to live on Earth, and to explore the stars. As we begin to see the universe not as a distant, unfathomable place, but as a connected network of planets and stars, our sense of belonging expands. Earth is no longer the center of everything. Rather, it is one small part of a vast and interconnected cosmos. The discovery of exoplanets forces us to consider our place in that larger picture, and to confront the fact that we are not the only inhabitants of the universe. As we continue to explore these distant worlds, we are also confronting larger questions about the nature of life itself. Are we truly unique, or is life a natural outcome of the universe's processes? If we find other civilizations or life forms, what does that mean for our understanding of our own origins and our future as a species? The discovery of exoplanets brings us closer to answering these questions, but it also raises new ones, pushing the boundaries of our imagination and understanding. Ultimately, exoplanet discoveries are about more than just finding new planets. They are about finding meaning in the cosmos. They remind us that we are part of something much larger than ourselves, a universe full of possibilities, waiting to be explored. Whether we find life on other worlds or not, the search for exoplanets helps us understand our own existence and our place in the grand narrative of the universe. And in that journey, we may find not just new worlds, but new ways of thinking about life, connection, and home. The discoveries of exoplanets have ushered in a new age of exploration and discovery in the field of astronomy and space science. What was once a speculative idea, whether other planets could exist around distant stars, has become a rapidly expanding field that has already unveiled thousands of planets in our galaxy alone. These discoveries are reshaping the future of space exploration, pushing the boundaries of what we know about planetary systems, the potential for life beyond Earth, and the conditions that might support such life. The implications of these discoveries are vast. As we continue to find planets in the habitable zone, where conditions might allow liquid water to exist, we are beginning to see a universe teeming with possibilities. Each new exoplanet discovered adds to the ever-growing list of potential homes for life, some of which may share conditions similar to those on Earth. Whether these planets host life as we know it or harbour entirely alien ecosystems is still an open question, but one thing is certain. The quest to answer that question will guide the future of space exploration for decades to come. One of the most exciting aspects of exoplanet research is how international collaboration has played a vital role in advancing our understanding of these distant worlds. NASA, the European Space Agency, ESA, and other space organizations have teamed up on missions like the James Webb Space Telescope and SHIOPS, a mission focused on characterizing exoplanet atmospheres. By pooling resources, knowledge, and expertise from across the globe, these organizations have been able to push the envelope of what is technologically possible, allowing for more ambitious missions and more detailed observations. This international collaboration is crucial because the study of exoplanets requires more than just cutting-edge technology. It requires the collective brainpower and dedication of scientists, engineers, and researchers from all corners of the world. As space exploration continues to grow, this global cooperation will only become more important. The sharing of data, resources, and expertise not only helps accelerate the pace of discovery, but also fosters a deeper sense of unity as humanity embarks on the shared goal of exploring the cosmos. Looking ahead, the search for habitable planets and signs of extraterrestrial life will continue to evolve. As technology improves, we will develop more sophisticated ways to detect and study exoplanet atmospheres, looking for biosignatures, chemical indicators that could reveal the presence of life. The James Webb Space Telescope will be a game changer in this regard, enabling us to detect faint signals from distant planets with unprecedented precision. But beyond the capabilities of current technology, the next few decades could bring about new breakthroughs that allow us to explore exoplanets in even greater detail, uncovering information that could reveal whether life, in any form, exists beyond Earth. As we search for life, we may also discover new insights into the origins of life itself. The conditions that allowed life to emerge on Earth are still not fully understood, but studying exoplanets could help answer some of these long-standing questions. By examining planets with different atmospheric compositions, temperatures, and chemical environments, we can learn more about the potential paths that life might take and what factors are crucial for its development. Even if we do not find definitive evidence of life on another exoplanet, we will gain valuable insights into the fundamental processes that have shaped life on Earth. Looking beyond the immediate goal of finding life, exoplanet research is also pushing us to redefine the very concept of home in the cosmic context. Earth has long been viewed as our one and only home, the unique planet where life took root and thrived. But as we find more and more planets that resemble Earth, whether in terms of size, temperature, or atmospheric conditions, the idea of home begins to expand. If there are potentially habitable planets out there, how do we reconcile our place in the universe with the possibility that life could exist elsewhere? How does this affect our sense of identity, our responsibility toward our own planet, and our view of humanity's future in the cosmos? The discovery of exoplanets challenges us to think about humanity's future in a new light. The possibility of colonizing other worlds, once considered science fiction, is now a topic of serious discussion. While the challenges of reaching and colonizing an exoplanet remain immense, the search for habitable planets offers a potential avenue for humanity's long-term survival. Whether or not we eventually colonize an exoplanet, the pursuit of understanding these distant worlds is an essential step in securing humanity's future as a spacefaring species. Exoplanet discoveries also raise important ethical and philosophical questions. As we search for life, we must consider the implications of potentially discovering intelligent extraterrestrial civilizations. How will we approach such a discovery? What responsibilities will we have to protect other life forms and preserve the integrity of their environments? The search for exoplanets is not just about finding other worlds. It's about confronting the broader questions of what it means to be human in a universe that may be far more crowded and diverse than we ever imagined. Ultimately, the discoveries of exoplanets represent a stepping stone for humanity's broader exploration of the universe. While we may not yet have the technology to send humans to distant exoplanets, we are laying the groundwork for future missions that will one day make interstellar travel a reality. The technologies we develop to study exoplanets, such as advanced telescopes, propulsion systems, and life support systems, will have far-reaching applications, not just for space exploration, but for improving life on Earth as well. As we continue to study exoplanets, we are not just learning about other worlds, we are learning about our own. Each discovery brings us closer to understanding the conditions that make Earth unique, while also challenging our assumptions about what makes a planet habitable. We're beginning to see the universe not as a distant, unapproachable place, but as a network of interconnected worlds, some of which may one day serve as humanity's new home. The future of space exploration is bright, and the search for exoplanets will continue to be at the forefront of this exciting journey. Whether we find life or not, these discoveries will deepen our understanding of the universe and our place in it. As we look to the stars, we realize that the possibilities are infinite, whether in terms of scientific discovery, technological advancement, or the potential for human settlement on other worlds. The journey has only just begun, and the future of exploration is limitless. The discovery of exoplanets is just the beginning, and it is one of the many steps that will lead humanity to new frontiers in the cosmos. As we look at the incredible strides humanity has made in the field of exoplanet discovery, it's clear that we are only just beginning to scratch the surface. From the first detection of a distant planet orbiting another star to the thousands of exoplanets we've discovered since, each new finding has opened up a vast array of questions, each one more fascinating than the last. The search for planets beyond our solar system has not only transformed our understanding of the cosmos, but it has also redefined the way we think about life, our place in the universe, and the future of humanity itself. The scientific journey of discovering exoplanets is ongoing, and with every new observation, we inch closer to understanding the true diversity of planets that exist across the galaxy. We are no longer limited to our solar system when imagining worlds. We now know that planets can come in many forms, from gas giants and super-Earths to water worlds and rocky planets in the habitable zone. Some may even harbour conditions that could support life. The technologies that have made this exploration possible, such as the Kepler Space Telescope, the James Webb Space Telescope, and upcoming missions like TESS, continue to evolve and improve, opening up even more possibilities for the future. But as we push further into the cosmos, we are also faced with deeper, more philosophical questions. The discovery of Earth-like exoplanets forces us to reconsider our place in the universe. Are we truly unique, or is life something that can emerge across the cosmos under the right conditions? The search for life on other planets challenges our assumptions about what makes Earth so special and, in many ways, humbles us as we realize that we may not be the center of the universe, but merely one small part of a much larger cosmic story. This journey is also reshaping the way we think about the future. While the discovery of exoplanets has already ignited our imagination, it also holds the potential to impact the future of space exploration in profound ways. The possibility of interstellar travel, colonization of exoplanets, and the development of new life support systems all hinge on our continued exploration of these distant worlds. Technologies that are currently in the early stages, such as nuclear propulsion and light sails, could one day allow us to reach these far-off planets and begin a new chapter for humanity beyond Earth. In this sense, exoplanet discovery isn't just about answering questions about life elsewhere, it's about preparing for humanity's future in the stars. And yet, despite all the technological advancements and knowledge gained, we still find ourselves asking the fundamental questions. What does it mean to be human? What does it mean to find life beyond Earth, or to make another world our home? The discoveries we make about exoplanets, their atmospheres, and their potential for supporting life ultimately lead us to confront our own origins, our place in the universe, and what the future holds for us as a species. While we may not have all the answers today, the ongoing search for exoplanets reminds us that the universe is full of endless possibilities. Every exoplanet we discover adds a new layer to our understanding of the cosmos. Even if we never find another Earth, the knowledge we gain from studying these planets, how they form, how they evolve, and how life could potentially exist in so many different ways, will continue to shape our scientific pursuits and our philosophical outlook for generations to come. In many ways, the discoveries of exoplanets are just the beginning. As we continue to explore these distant worlds, we are learning more not just about other planets, but about Earth itself. The processes that shape planets, their atmospheres, and their potential to support life offer invaluable insights into the origins of our own planet and the future of life here. We are gaining a broader perspective on what makes a planet habitable, and, perhaps more importantly, what makes life possible in the universe. As we look forward to the next chapter in the exploration of exoplanets, we are reminded that the future is filled with endless discovery. New technologies, new missions, and new insights will continue to expand our understanding of the universe and our place within it. And with each new discovery, we are reminded of the incredible mystery and wonder of the cosmos and how much there is still left to learn. So as we continue this journey of exploration, we invite you to stay curious, to keep learning, and to never lose sight of the infinite possibilities that lie ahead. Whether it's the discovery of new worlds or the quest to answer the fundamental questions about life in the universe, the exploration of exoplanets is only the beginning of what promises to be a thrilling adventure. The stars are calling, and humanity's journey into the cosmos has only just begun.